Welcome to Spring LIB.
This question deals with two specific gas laws. One is Dalton's law of partial pressures, where the sum of all the partial pressures equals the total pressure. And then the other one ends up being Gay-Lussac's law, where the pressure divided by the temperature for one set of conditions is equal to the pressure divided by the temperature for a second set of conditions. For this particular scenario, we have carbon dioxide and water in a 3:1 mole ratio. We don't know the size of the container, but we'll realize that that won't be important. The temperature is 200 degrees Celsius, and the pressure is 2 atmospheres. So we can state that the total pressure in this container will be equal to the partial pressure of carbon dioxide plus the partial pressure of water, this being Dalton's law of partial pressures. We know that this total pressure is given to us as 2 atmospheres. We also know that the mole ratio is 3 moles carbon dioxide for every 1 mole water. Assuming both of these behave ideally, the ratio of pressures is equal to the ratio of moles. Using the ideal gas law, you can prove this to yourself. So the ratio of CO2 pressure to H2O pressure is equal to the mole ratio of CO2 to H2O. So knowing this, we can state that we have 3 times as many moles of carbon dioxide as we do water vapor, or that the pressure of carbon dioxide is 3 times the pressure of water. This now allows us to substitute into this equation carbon dioxide pressure or water pressure. Because we're interested in carbon dioxide, let's rearrange this equation and solve for the pressure of H2O and realize that it's 1/3 the pressure of carbon dioxide. So we can substitute in here for the pressure of water 1/3 the pressure of carbon dioxide. This sum then is going to be equal to 2 atmospheres. This ends up being 1.333, repeating pressure of carbon dioxide is equal to 2 atmospheres, or under these set of conditions, we have a partial pressure of carbon dioxide that is equal to 1.50 atmospheres. So hopefully it makes sense then that the pressure of water would be 0.5 atmospheres. Then what happens is we cool the temperature. We keep the volume the same. All we're doing is changing the temperature from 200 degrees Celsius to 10 degrees Celsius. In the process, we retain carbon dioxide as a gas, but the water vapor comes out as liquid water. We'll ignore the volume change that occurs when water comes out as liquid water. We can now look at the Gay-Lussac's law. Gay-Lussac's law says that the pressure under the first set of conditions divided by the Kelvin temperature under the first set of conditions will be equal to the pressure of the gas under the second set of conditions divided by the temperature, the Kelvin temperature, under the second set of conditions. This is assuming that the volume is constant and the moles of carbon dioxide are constant, and both of these are constant in this given scenario. We can rearrange this to solve for the pressure when the temperature has changed to 10 degrees Celsius. So P2, I'm using this to correspond to the second set of conditions where the temperature has now decreased from 200 degrees Celsius to 10 degrees Celsius. So to solve for the pressure of carbon dioxide under the second set of conditions, we simply need to know its partial pressure under the first set of conditions, which we just determined was 1.50 atmospheres. The second set of conditions temperature is 10 degrees Celsius, but we need to know its Kelvin temperature, so it'll be 10 plus 273. We then divide that by the temperature under the first set of conditions, which is 200 degrees Celsius, but we need it in Kelvin, so we add on 273. This then gives us a carbon dioxide pressure when the temperature has been decreased to 10 degrees Celsius and all the water vapor has come out of 0.897 atmospheres.